I thought we'd talk about a paper which came out recently, which has astronomers scratching their heads somewhat. It's called A Population of Red Candidate Massive Galaxies Approximately 600 Million Years After the Big Bang.
Nice title.
And it's come out of the very recent JWST observations. So obviously it's kind of right at the cutting edge of what's going on now in studying galaxy formation. Okay, I guess we need to go through what it is that they've done before we can figure out why it's weird or why it's sort of a little bit problematic. So I need to draw a picture. So it's talking about the properties of atoms and the fact that they have these discrete energy levels. There are only certain energies that the electrons around an atom can have. And in the case of hydrogen, it's particularly simple because you've only got one electron to worry about what energy it's got. And so physicists draw these things called energy level diagrams, which are just basically telling you what the allowed energies the electron can have. And they kind of get closer and closer together. So you go up, so you've got kind of basically you've got energy increasing that way. An electron has to be in one or other of these energy states. So if you've got a load of hydrogen, wherever it is, but we're thinking about the distant universe, it'll generally be in this lowest energy state. And so if something were illuminating this gas, say behind it, and lighting it up, the electrons here could jump up if the light had just the right energy from there to there, for example, or to a higher energy state and so on. And what that means is if we had a spectrum, so if we're measuring how bright the object behind this gas is, measured depending on its wavelength, if there were no gas in the way, then you just see kind of a broad spectrum of light to do with how hot that gas is and so on. But because some of the light is now being absorbed by this material at these very particular wavelengths, then actually you end up seeing these dips in the spectrum at these particular wavelengths. And there's a whole load of them that we can have, but you can see eventually you reach a point where there are no more energy states. That basically is what happens when the atom is being ionized. It will actually rip the electron right out of the atom. And now we're free to pick any energy you want up here, because there aren't particular energies that are allowed. You can have any energy you want when you're kind of ripping the electron out entirely. And what that does to the spectrum is it means that anything that's higher energy than that jump there will tend to be absorbed. So energy translates, when the energy is higher than a particular value, that means the wavelength is less than a particular value. And so all the light on that side gets absorbed. So you end up seeing kind of an edge here that you lose all the light, because any light that had wavelengths this short will have energy enough to rip the atom apart. So this is one of these things called a break or an edge. And transitions from this lowest energy state are called Lyman transitions. Breaks are really good if you're an astronomer, because the way we figure out how far things are away is by measuring their redshift, right? Measuring how much the light's been shifted to the red, because what happens is something some distance away will emit light towards us. As it's traveling towards us, the universe has been expanding. That stretches out the light, which makes it redshifted. So if something's further away, the light will have been traveling for longer, which means the light will have been stretched out more, which means it'll be more redshifted. So we can translate the redshift directly into how far away something is. One of the problems when you look at things in the very distant universe is that they're very faint. So measuring redshift is a hard thing to do. When things are very faint, you really can't get a nice spectrum like this. But edges are easier to measure, because if you think about what happens, if instead of having a spectrum, if we just measured things in kind of broad terms of, say, we've measured where the red light was and where the green light was and where the blue light was. And if you think about taking a whole series of images at over different bands, what you'd see is you'd see the object here, but then when you started using bands over here, all the light's absorbed, and so the object will disappear. And so something where there is a strong Lyman break like this, you'll have this effect called a Lyman dropout, that basically the object will just disappear when you start measuring things at bluer wavelengths than that. The other thing, of course, that's going on is that the whole spectrum gets redshifted as you look to more and more distant objects. So in the rest frame, when the light was actually being absorbed, this feature is in the ultraviolet. But when you start looking at things in the more and more distant universe, that break shifts to redder and redder wavelengths, which means that instead of being in the ultraviolet, it becomes into the optical, and then actually it moves into the near infrared as well. So I can show you some examples from this paper. So this is a whole series of images taken with JWST at different wavelengths, working their way to bluer and bluer wavelengths. And you can see there's an object which is stormingly bright and then quite quickly just disappears. It's vanished entirely in these last two frames. So each of these images is working their way from, starting in the infrared and working their way towards the optical part of the spectrum. And so at some point you reach a point where the light becomes blue enough or less red enough that actually the objects just disappear. This is a great way of identifying very distant galaxies. It has a couple of sort of shortcomings. The first shortcoming is that you're essentially identifying galaxies from the light that when it was emitted was in the ultraviolet part of the spectrum. That ultraviolet part of the spectrum is very high energy light, and in terms of what stars produce it, it's only very massive, short-lived, very bright, very hot stars. And it doesn't take many of them because they're so bright that actually a relatively small number of them will produce a load of ultraviolet radiation which can then be absorbed, so you can then detect it in this way. So to infer from that the global properties of a galaxy is kind of a challenging thing to do, because it's really not telling you much about the galaxy. The second snag is that there are various other breaks at other wavelengths. And if you're not careful, you'll identify something as a break, that something is nice and bright and then suddenly gets very faint, and identify that as this Lyman break, but it could be another break. It could be something else going on elsewhere in the spectrum, and you'll end up attributing completely the wrong redshift to this galaxy and end up with complete nonsense. So those are the two snags. This paper very neatly gets around it, doing something that we've only just been able to start doing with the James Webb Space Telescope. And in particular, everything I've just told you about happening from this lowest energy state can happen from the next energy state up. If there are a load of atoms that are in this slightly higher energy state, then again, there'll be absorption at various wavelengths. But eventually you'll reach the point where the atom gets ripped to pieces, the electron gets ripped out entirely, and so you'll have exactly the same kind of feature. And that's called a Balma break, because emission and absorption from this second energy level is called Balma lines. And so actually there's this kind of Balma break when atoms are being ripped apart. In some sense, that will be a killer thing, in that if you've identified a galaxy by this Lyman break, but if you also see this Balma break in the spectrum, then you've got two features. And now you're pretty sure, actually, I know what's going on, because these two features, they're a fixed wavelength apart. And therefore, actually, the fact that I've identified both features really means I know what I'm looking at, that's the Lyman break, that's the Balma break, and we understand what's going on. The reason why we haven't been able to do that before is that if you move the Lyman break all the way into the near infrared, which is kind of the most distant we've been able to do in the past, the Balma break shifts all the way into the mid-infrared. And we haven't had a telescope that could record data of the quality needed to identify breaks in the mid-infrared as well as in the near infrared. JWST can do both. And so they've actually been able to identify what they call double break galaxies. Here's some of these plots of showing what the intensity looks like. So this is how bright these galaxies are, and this is the wavelength that they're looking at. The red line is kind of a model, but the little points you can see on here are the images they've actually recorded, how bright the galaxy is at these different wavelengths. And these two here are actually upper limits. They didn't detect the galaxy at all there. And so here, this is the Lyman break, where you go from nothing at all to suddenly being able to see the thing. And then there's a second step up. This is the Balma break. And it's a much smaller feature, but it's definitely there. There is a significant step up at that point. When you've got data like this, firstly, you're really pretty confident that you have identified a galaxy at those very great distances away, because you've nailed down these two break features, which are telling you what the redshift really is. But the second thing is that now you're not just reliant on the ultraviolet light, because you've got this data all the way. So this was the ultraviolet effects of the galaxy. But by the time you're over here, in the mid-infrared, that was light that was emitted in the optical part of the spectrum. And the optical part of the spectrum is telling you not about those extreme, ultra-bright, ultra-massive stars. It's telling you about bog-standard stars in the galaxy. And so by studying the properties of these galaxies, now looking at these bog-standard stars, you can actually learn a lot about what the properties of the galaxy are, like what the mass of the galaxy is, for example. Because if you've just got those ultra-luminous, very massive stars, it doesn't tell you much about what the total contribution to the mass of the galaxy is. It's just telling you there are a few very massive stars. Whereas by the time you're looking at this sort of mid-infrared data, which is telling you about the optical part of the spectrum, that's telling you how many stars there are like the sun. And that can fairly directly translate into how massive these objects actually are. So the problem is that there are two things. Firstly, these galaxies, as you can see, they're relatively red, right? There's quite a lot of light coming out in this red part of the spectrum compared to what's coming out in the blue part of the spectrum. And as I said, they describe it in the title, right? It's a population of red candidate massive galaxies. So both of these are the problem. The reason why red is a problem is because the spectrum of a galaxy only becomes red when it's no longer dominated by those very young, very blue, very hot stars. So when you see a red galaxy, that's telling you that that galaxy's been around long enough for all those very massive, very blue stars to have gone through their complete life cycle, blown up a supernovae, gone away. And that sets a limit as to the age of the galaxy. Right? A galaxy has to be, in order to have reached that stage of maturity, it has to be a few 100 million years old at least. And that's getting a little uncomfortable, because here we are identifying galaxies 600 million years after the Big Bang. And yet they're already 200 million years old. So that means they have to have been formed at the latest sort of 400 million years after the Big Bang. And so that's pushing the formation of galaxies back really quite close to the Big Bang. In the grand scheme of things, the universe now is 13.8 billion years old. So a few 100 million years after the Big Bang is really kind of almost the blink of an eye. Somehow you're making these galaxies. And then not only are they oldish because they're red, but they're actually massive. When you go through this process of translating how much light there is there into figuring out how much mass there is, you end up with these galaxies being about sort of 10 to the 10 times the mass of the sun. So 10 billion times the mass of the sun, which is a respectable sized galaxy, right? That's sort of a tenth as massive as the Milky Way. So not only do you have to make these galaxies very close to the Big Bang in relative terms, but somehow you have to make them very massive. And since the way we think galaxies form is by sort of mass kind of accreting, being pulled together by gravity, we expected that galaxies would kind of build up quite slowly, that the first galaxies that you're seeing would be quite low mass ones, and then over time they merge with each other or they acquire more material through gravity and they build up to the kind of things that we see today at a much slower rate. So seeing very massive, quite old galaxies that close to the Big Bang is really pushing things really quite to the limit in terms of our understanding of how galaxies form.
I mean, something could be wrong.
Yeah, and so there were two, and fundamentally there were two things that could be wrong. The observations could be wrong or the theory could be wrong, right? Well, the observations aren't wrong, but I guess it's the interpretation of the observations could be wrong. It could be, for whatever reason, we really don't understand these breaks the way we think we did, or somehow the way we're translating the amount of light into the amount of mass is wrong. So there are ways that the way we're interpreting the observations could be wrong, or it could be that actually our understanding of how galaxy formation works and the simulations we're doing of those early stages of galaxy formation just aren't quite right, and there's some extra bit of physics that we haven't put in there yet. So you're right, some things, things are sufficiently in tension now that it's going to break and something has to be wrong.
One of my favourite things about galactic astronomy is how lovely galaxies look and the images that come with it. I always feel a bit sad when I see looking at all the galaxies reduced to a graph.
Yeah, and actually, now we look at, even with the power of the James Webb Space Telescope, we're looking at things which are so far away that if we just go back to the picture of their picture, they're not very exciting, are they, really? This is why I study nearby galaxies, right? Because I like looking at those beautiful spiral arms and all the other elegance of the nearby galaxies. And unfortunately, even with JWST, we're not getting to that level of beauty in these distant things.
Well, I want to talk about the physics behind how you actually get a telescope like this to point in the direction that you want it to.
But as you squeeze atomic gas together, you start actually turning it into molecules, start producing molecular hydrogen as well. So the reason why astronomers are very interested in molecular hydrogen is that that's usually the density of material that turns into stars.